So, hello coders, welcome to my YouTube channel. Today we are going to solve the problem of the day of 19 January. So, let's go through the question, what questions tells. So, basically it's 1292, that is maximum side length of a square with sum less than or equal to threshold. So, let me go through the question and I'll explain you the question, then we will go through the answers. So given m cross n matrix mat and integer threshold, so return the maximum side length of a square with sum less than or equal to threshold or return 0 if there is no such square. So basically we have been provided a matrix. So suppose you can see the example here. We have been provided a matrix of size 3 cross 7 and you have been provided the value threshold value, that is 4 here, and also the values provided here in the matrix. So you have to find squares, like a squares have like same length and same breadth. So basically the row size and column size should be same. So we have to find a matrix where row size or column size should be same, that is the square, where the sum of all values inside that square must be less than or equal to the threshold. So if you find such squares, then you have to find the maximum side length of that square with all the possible squares. Otherwise, if there is no any possible squares, then you have to return 0. So here we can you can see in the example that if you will start from the 0th index, then it has been figured out that you have a square of size 2, which sum, if you will see the sum, then it will be 1 plus 1 plus 1 plus 1, that is 4, which is less than or equal to threshold because 4 is equal to threshold value. So it one square of length 2 is possible, and one size is also possible, because if you see a square at 0 0, so that will be size of only one, and that will can be also be possible. So how will you be approach this? So if you think brute forcefully, like in the brute force way, so you can, what you can do, you can just try to go through all the indexes, like all the cells. So for example, if I am at I comma j, then I will have I will do in the brute force, that I will try to find all the squares possibles. So that will give me all the squares of length 1 2 till whatever length is will be there. So if we can find all the squares possible in this matrix, then we can just find the sum of present, like sum of the values present in that squares. And if we are able to find the values present in that square, then we can just sum it. And if that sum is less than equal to threshold value, then we can just check if we can maximize if we can maximize that length of the square or not. So this is the brute force way. So if you try to see like this, for example, if you are started iterating from uh, 0 to n minus 1, and then after 0 to m minus 1, so this will take O of n square to reach you a particular cell. So then you will reach to a particular cell, suppose I comma j. Then after you can start from here, that yeah, find a square starting at I comma j. So if you are at I comma j, if you are at I comma j, then you will start finding the all the squares of 1 comma 1 cross 1 till k cross k. Suppose k is the maximum length of the square possible. So this way you will do the maximum length of the square, you'll and this will provide you the maximum length of the square. But if you'll see the time complexity of this solution, then it will be like O of n to traverse the first row and O of m in to traverse the column X. So if you will reach till ij, then it will take you in a square, and inside that also you have to traverse through the squares. So and you will have to find the values of that values inside that square. Then it will also take you O of n square. That means O of n to the power 4 will be the solution, brute force approach, which is not feasible for this. So as you can see in the constraints, the m and n can be 300. So this cannot be feasible. We can solve till O of nq or O of n square log n if it's given in the 10 to power 2 or till 500. So we will think something like different, like can we optimize this third step, like what we were doing, that if we can optimize this if we can optimize this value, then we can improve the time complexity to O of NQ. So just think, how can you find the find the all squares of length 1 to 1 length 1 till maximum length possible. So if and also if you will see, the time is not taken by this traversing from 1 to k. Instead the time is will be taken by the sum which we will find inside that traversal, because we need to find the value, we need to find the sum of the values present in that square. So that will take O of n square. So if you will just try to see differently, that if we can do, if we can optimize to find the sum of any square matrix, a square submatrix, then it can be decreased, its, its time complexity can be decreased from O of n square to O of n to the power 4 to O of nq. So to optimize this, we can think of the like a prefix matrix sum. So what if you are not aware about that prefix sum, so prefix sum basically helps to find a sub array sum or sub matrix sum. For example, if you have been provided an array of one like this, 1 5 3 2 3 2 6 7, and if you are told to find the sum from index 1 to index 4, then in the one way you can just do the traversal from 1 to 4, and the one other way is, if you have given multiple queries to find the sub array, then you can just use a prefix sum. So basically prefix sum, what prefix sum does is it just stores the sum till ith value. Suppose here I can just keep summing till the last index. So 1 plus 5 will be 6, 6 plus 3 will be 9, 9 plus 2 will be 11, 11 plus 6 will be 17, and 70 plus 7 will be 24. So basically it forms a prefix sum, and if you have been provided to find the sum from I barabar 1 to I barabar 4, so basically what you can do, that you can just take the prefix of last index, that is 4, and you can just subtract the index value, subtract the sum value till till l minus 1, that is left. Suppose this is the left side and this is the right side. So what you can do, you can just subtract prefix of uh, l minus 1 from r's, which will be, then you will get the mid sum value. So basically here it will be prefix of 4 minus prefix of 0, which will be the 0, 1, 2, 3, 4. So basically it will be 17 minus 1, that will be 16. So this is the basically the prefix sum. So in array you can do like this, but similarly we can also do this in the matrix. So there's just one difference in the matrix. Basically, let me take the first example. Yeah. So what we will do in the matrix, basically we will try to keep all the sum till I. If I am at I comma j, then I will just it will keep keep the sum of all values from 0 comma 0 to I comma j. So this will just store the sum till I comma j. And if you have been provided to if you been provided to find the sum from I1 comma j1 to I2 comma j2, then you can easily find the find this sum in just O of 1 of. So let me go through the approach what you will do in the just generating the prefix matrix. So let me just generate the prefix matrix. Firstly, you will just do the summation of all the rows just like the array, and then it will form like this. So if you will just do the summation of first row, then it will form 1, 2, 2, 3, 5, 5 to 7, 7, 3, 10, 10 to 12. So is it fine? 1, 1, 2, 2, 3, 5 to 7, 7, 4, 11. Sorry. 11, 11, 3, 14, and 14 to 16. So actually second and third row is also same. So I'll just copy paste this second and third row. After this, you can see that you got the prefix sum of each row. Now you just do the prefix sum of each column. So if you do the prefix sum of each column, that will form the first column will be the first row will be same. If you do the with the second row, then it will become 2, 4, 15, 14. It will become 14. It will become 22. It will become 28. It will become 32. And if you will go on the third column, um, if you go on the third column, sorry, if you go column wise for the last row, then it will become 3, it will become 6, it will become sorry 10, I think it will become 15, it will become 21, it will become 33, and 14, 28, and 14 will be 42, and it will be 48. So this is the prefix matrix you have calculated from this summation. After that, you can see that this matrix will just provide what I told on the line 25, that it will keep the sum of all values from 0 to 0 to ij. So if you are trying to find, suppose you have wanted to find the sum of values from 1 comma 1 to 3 comma 4, sorry 2 comma 4. So 1 comma 1 will be here 4, and 2 comma 4 will be 0 1 2 0 1 2 3 4, like 33 till here. So I'll just get the sum of 33. So the total sum will be 33. But this is not the final prefix sum, this is not the final sum matrix sum from 1 1 to 2 4. We need to subtract the previous value. So basically if you'll see here, like this, till 33. You need to subtract this value and this value, the upper value, 2 and 3. And so what I can do is I can just subtract the left side of this ith value, like 1 comma 1, like the sorry, the jth value. J is 1 here, so I'll just remove all the values present on the left side of this j. And similarly, I'll also try to remove all the values above that ith value. So remove the values which are present on the left side. So basically, I'll remove 3 from here. Also, I'll remove the upper value, that will be 11. But if you'll see, I have removed this value and the upper value and the left side value. Then if you'll see that the this one has been removed two times, so I need to add one more time to get the prefix sum, final prefix sum. So I'll just add one in the final result. So this will just make the sum 33 minus 3, 30, and 11, 3, 14, 33 means 20. This is 20. So we got the total sum 20. But and also if you'll see in the original matrix, starting from 1 1 to 4. So this will be 1 3 4 4 to 6 6 14, and similarly here also you'll get 10 from this cell to 4. So that will be 20. Yeah, so this way we can calculate total sum, and we can check the boundary for 0 and the n minus 1. If the value is if the value I'm checking from the first column or first row, then I will not subtract any values on the left side or upper side, because it will not be present there. So basically we'll get the prefix sum in this way in O of 1 if you will calculate the prefix matrix. So this is the main calculation here. So now we will do what we are doing at the starting. We'll do the same thing. This is the second approach we are doing. So we are doing here 0 to n minus 1, then 0 to n minus 1, and for ij I am just trying to iterate from 1 to k, 1 till k, and I am just trying to get all the prefix sum possible, uh, all the prefix sum possible, like all the prefix value which will be for possible squares. So it will give me just in O of 1, and this will be O of n. So this will time complexity will be O of nq. So let me now explain you the code for this O of nq solution. So come here, like so coming to this side, I've just taken the row size and column size of this matrix, and sorry, not this one. So yeah, this one. Sorry. Yeah. So basically, yeah, here I have calculated the prefix matrix. You can see that I've just calculated all the whole rows value, and then after I've calculated the columns value, which will compute me the prefix matrix which I told you. And after that I iterated for ij, and what maximum what maximum side we can get from starting from ij, which we can be calculate from taking minimum of n minus I and m minus j, which will be the maximum, what maximum side length we can get. That will be the minimum of n minus I and m minus j, because it is the matrix, not the square. So it's an even size. So we need to check like what maximum square size can key generate. So starting from, actually we can go from 1 to n, like 1 to the minimum value, that maximum square size, but we can just do the reversal way because we need to find the maximum value. So if we get the maximum k first, then we can just break down from it there. Or if the I've also initialized the answer with 0. So if answer is already greater than this k value, then we don't need to go further. We have already calculated earlier greater than this k value, so we don't need to do anything else. We'll just break from here. We'll just check for another squares. So now I have taken the last I1 J1, that is the I1 J1 is basically the last value, which will be the total sum. And if j greater than 0, then I'll just subtract the left side of the value, and if I greater than 0, then I'll subtract from the upper side of the value. And as I told you that the top value, like top submatrix, has been removed twice by this way. Then I'll just add one time of that prefix of I minus 1 and j minus 1. And if that total sum which I got in through this prefix sum calculation, if that value is less than equal to threshold, then I'll just change the answer by k plus 1. Basically we are taking that 0th index, so I'll just do k plus 1 and break from here, because we don't need to check the smaller value because we already get the bigger value. So this way we can do the final answer, and this will take the time complexity of O of NQ. So basically this is the, yeah. So we can do this way, and but we can also improve here. You can see that we are doing this. We can just improve this in more efficient way. Let me show you how you can do in better way. So basically, if you'll see here, we are just checking all the possible solutions which are taking work in queue. We can like do in the terms of binary search. For example, if I am checking, I started taking from all the all the, suppose I have at kth, I'm checking, I have to check for the kth side. If I have to check third approach, that is binary search approach. If I have to check for the k size square, then I will just iterate through the all the values, all the values starting from, if you'll see, I have to iterate and find all the possible squares which are of k length, which will take just of O of n square to find that. Yeah, because you can see here, let me just show you what we were doing. You can just see here, we are doing O of n square here, and k barabar m n minus 1 to k barabar 0. So basically we are just doing this k solutions, we are doing this k times. So if you will do just one times only for k, only for kth value, then it will just take O of one time. So basically we can say that if we have been given k size square, then we can find if it is possible to get k size square or not. And if it's possible, we can also get a smaller size, and if not possible, we can check for less size than k. So basically this is the approach. So it will take O of log n into n square, because log binary search takes log of n, and for to check every time uh, we will just take O of n square. So if we start from like this, let me go through the solution once. Here, here I have done in the similar way using binary search. So if you'll see, let me copy this my solution so I can explain you this in better way. Yeah. So here I have done the same thing, that I have calculated the prefix matrix in the previous as in the previous solution, and after that I have doing the binary search by taking the minimum and maximum length possible, like minimum maximum square length possible. So maximum square length can be possible like minimum of n comma m. So because we cannot take like we cannot generate, if you see the example one, you cannot generate maximum like a square size maximum than 3, because we cannot go beyond 3 on the row side. So that by we have taken minimum of n comma m plus 1. This is the just I'm taking just bound, because I'm checking binary search in this way, like e minus is greater than 1, that which will just give me directly the answer. We are not I'm not checking like is less than equal to e. I'm checking in different way. So here I have taken mid, and I've created a function which will just check that if it's possible to create case size or not. If it will be possible, then I'll just uh, go to the right side, that I'll change the s to mid, and if it's not possible or to go to the left side, then I will change e to the mid. And at last, if everything will be present, like at last if the e and s becomes same, or it becomes like consecutive, then I've just got the my maximum size of the square. And also if we are not able to find, then s will always be 0, and it will be decreased to 1. So here the final, like the return 0 if there are no square, will also verify this condition, like it will also satisfy this condition. So I'll just return s at the last. Now let's see check method, what we did. So in check method I have taken k, that is the mid value, and the v, that is the prefix matrix which we have calculated, and the threshold value to compare the with the threshold. So we are just calculated the row and column size. After that, I started to go from 0 to n minus k. Basically, n minus k just to make sure that we are not going beyond the possibilities, beyond the bound. And similarly here also 0 to 0 n minus k, because we need to find the size, square size of k length. So here I have taken the last index I plus k minus 1, and j1 is equal to j plus k minus 1. Which is basically here, if you will see 2 4, so basically like this 33. Similarly, we are calculating the last squares. So there I'll calculate the total sum, and I'm doing the same way. So if we have to subtract the left side, upside, then we will subtract the upside. If you have to subtract the left side, then we will subtract the left side. And if you both done, and if both are also like both are also possible, both were possible, then we need to just add one more time, like the like upper sub matrix we need to add, because we have subtracted that 2 times. And after that, if that total sum we calculated is less than equal to threshold, then yeah, this is possible for this k, this mid value or k value, then we'll return true from here, otherwise we'll return false. So this will just take O of n uh, in like in log, sorry, in log n square, or basically we can say in minimum of n comma m, because we are taking minimum here. So minimum of n comma n. So this will take time complexity of O of minimum of m comma n into m into n. So this is the most efficient solution we can get. So yeah, I will share this link in the description. You can check my solution, or and you can check my solution in the description. That's it. Thank you.